All right, so before we start today's lecture, I want to apologize for not correctly explain sim hash. So basically, what I've been saying in Monday's lecture, I made a mistake. Okay, pi represents a half circle, which I incorrectly take it as the whole circle. So the conclusion is the same. Okay, the conclusion is correct. This is correct. But before we don't have, we only have one blue part, and the correct version where we should have two blue parts. So I will show you with a more vivid example. So using this tool, we can see how the value of A, or how the position of A actually affects the hash values, and how do we get the conclusion. So basically this red vector is vector A. Okay, the randomly generated normal vector. All right, so this dashed line represents the hyperplane. Well, it's in 2D space, so it's just a line, but in high dimensional space, it's a hyperplane using A as its normal vector. All right, so these two black vectors are X and Y respectively. Doesn't matter which is X, which is Y. Here, the hash value is the sign of A transport X and the sign of A transport Y. So the hash values could be either 1 or -1. And the geometric meaning of this is, say, X and Y, they lie at the different side of the hyperplane, or do they lie on the same side of the hyperplane? All right. So when they are at the different side of the hyperplane, as you can see here, their hash value should be different. And no matter how you move A, as long as they are at the different side of the hyperplane, right, the hash value would be different. But once, as you can see here, they lies on the same side of the hyperplane, their hash value would be the same. Right. So now it's pretty clear. I mean, if we consider all the different possibilities of this A, right? The only case that X and Y would have the same hash value is when they lies on the same side of the hyperplane. In that case, the hyperplane should only see either from here to here, right? That's one way, and also from here to here. So in total, it's 2 pi minus 2 theta, where theta is the angle between X and Y. So here comes the equation here. Right, so this should be the correct version. Or if you want, you can take only half the circle, and then it's theta over pi. So it's basically the same. All right. So that's for that's to correct the misunderstanding of sim hash. Now let's look at here. So as we have discussed last time, the problem of a single hash function, as you can see here, they're kind of too smooth, right? And it is hard to distinguish if two pairs have distances close to each other or not. So we want to control the ideal function. Ideal hash function would be something like this. It's similar to a sigmoid function, but it is not. We will see it later, but basically it's like for those close pair of objects or points, we want the collision. We want the probability that they share the same hash value to be large. Or on the other hand, if the distance is larger than R2 or they're dissimilar, we want the probability to be small as possible. All right. So here we use this P01, O2 to denote the probability of O1 and O2 should have the same hash value under a specific hash function, right? And this is apparently related to the distance between O1 and O2, or the similarity between O1 and O2. All right, now let's consider two scenarios because we're talking about and/or composition. So basically, as we have already seen that a single hash function may not be able to achieve what we want, so we are considering using multiple hash functions. So the way to combine multiple hash functions, usually either by AND or by OR. So by AND, we mean that we combine the k hash functions together, and you must match all the hashes. Then you can be considered as a match because it's an AND operation. You have to match all the k hashes to the query, say. Or for the 2 points, all the k hashes would be the same. All right, so in this case, what is the probability? Apparently, the probability is a simple math. So the probability would be the P of O1, O2 for a single hash function to the power of k. Now, if we consider using an OR operation, where you have L hashes together, since it is a OR operation, you only need to match one of the hashes. Right? It doesn't matter if you match more than one, but you must match at least one. Okay, and one is enough. All right, so in this case, the probability of O1 and O2 match with each other, or say considered to be to have same hash value under this special scenario. In order to compute this probability, we need to compute the probability of HO01 not equal to HO02, right? And use 1 minus this. So for this part, because we have L hash functions together and using OR operation, right? So they are different only when all the L hash functions they does not match, or they does not match any of the L hash functions. So the probability of the match on one hash function is P0102. So not match on one is 1 minus P0102. And you have L such kind of functions. None of them match. So to the power of L, this is the probability of they're not equal. So the probability of the equal is 1 minus this part. So here comes the equation right here. So let's have a look at user example to show how this actually affects the function, the hash function. All right. So we use min hash as an example because min hash is most straightforward one. So basically, the probability of O1 and O2 share the same hash value equals to their Jaccard similarity of O1 and O2. Right? So it's a straight line here. Right? If we use this AND operation with k equals to 5, this is what we end up with. So basically, we can see that for those dissimilar parts, right? This part, it's a dissimilar part. The probability is quite small, close to 0, and it increases drastically when the similarity becomes larger. Okay, so you would expect to see the same trend if we consider using a p-stable or using a sim hash. So basically, it's this is when the distance is large, when the distance is small. So it would be something like this. It would be something like this. This is for if we use distance. So if we use this OR scheme, this is the probability. The function would be something like this. So this part, as you can see, for the similar pairs, the probability of they share the same hash function would be very close to 1. But for those dissimilar parts, well, the probability is increased from 0 drastically to 1, as this part is smaller than 0.5. But if we take it pessimistically, I mean, the problem of this AND schema is that they're not large enough for the similar pairs, right? The probability is not large enough for the similar pairs. And for the OR scheme here, the problem is that the probability is not small enough for the dissimilar pairs. All right. So apparently, using either AND or OR does not achieve what we want exactly. We want something like this. All right. So LSH use a smart way to combine these two schemes together. Well, so the idea here is illustrated in this slide. So let's firstly define Hij. Any Hij would be a single LSH function, and this I is from 1 to L, and J is from 1 to K. So apparently I is for the OR operation, and J is for the AND operation. All right. So we firstly do the AND first. We do the AND first. So we define this big Hi of O, or we actually call it a super hash. This one is the concatenate of Hi1 to Hik. So it's a concatenate of k hash functions and using AND operation. All right. So it's quite similar to what we have done before. Then in this case, when Hi of O1 equals to Hi of O2, if and only if for Oj in the set of 1 to k, Hij of O1 equals to Hij of O2. Now this is the AND part. Right, for the O part, say considering the query Q and any data point O, say O is a nearest neighbor candidate of Q if there exists any I in 1 to L, well, this big I of O equals to big I of Q. So here we don't call it, we don't use the concept of hash function here because this OR operation is not that straightforward or that fit that. Sorry, this OR scheme does not fit quite well if we're using a hash concept. So basically here is that we're actually consider the query queue. We consider the query queue. And so O becomes a nearest neighbor candidate. If you still remember, we use we generate candidates first, and then we do the verification. Right. So the first step, we want to decide which point could become a candidate of Q. So O is a candidate of Q if there is I in 1 to L, the super hash of O and Q are equal. So the probability of this O becomes a candidate of Q because we do the AND first. So this is where this P QO to the power of K comes from. Because the probability of HIO equals to HIQ for any I would be the probability of Q and O to the power of K. And if we consider this OR scheme, as we have explained here, right? So it's actually 1 minus PQO to the power of K to the power of L. Right. Well, we want to make sure that this scheme is effective. Right. So here we use the example, we use K equals to 20 and L equals to 5. We will see how this probability of O is a candidate of Q changes with so here there should be no K here. Let me fix it first. So let's see how it changes with the probability of Q and O has the probability of a single hash function of applies on O and Q, and the hash values are the same. Right? This is what POQ stand for. So we use different values of PQO, and we compute the probability as here. All right. So as you can see, when the probability when the PQO is as small as 0.2, this, if we use this scheme, it makes it smaller, even smaller, right? And if it is large enough, like 1.9, the overall probability of O becomes a candidate of Q will be even larger, right? Very close to 1. And you can see it drastically changed at some point between 0.6 and 0.8, right? So here from 0.33 to 0.60 and to 0.86. So what does this number mean? For example, here as the last line, it actually means that we are expected to retrieve 98.8% of the data with, let's say, Jacquard is larger than 0.9. Well, for Jacquard is easier, but for the if we consider P stable or the Euclidean space, it just the distance smaller than a specific threshold. So let's look at the curve of this function. So basically, it is something like this. We can use different K and L to somehow change the curve, the shape of the curve, right? For example, if we want, say we want the threshold to be somewhere at 0.8. Say 0.8 is where we define the threshold for the similar points, right? Pairs, and we use 0.7 as the dissimilar pairs. All right. So as you can see, we can we can tune K and L, right, such that say the points, the pairs that the Jaccard similarity smaller than 0.7, the probability of such kind of such point or objects becomes the candidate is the probability is small, and for those larger than 0.8, it will be larger. All right. And apparently, as you can see, when the K and L are small, are both not that large, we can still do the similar things, but the space here, or the probability here, the probability here is not that desirable, right? And if we want to have a better, say the effectiveness, then we are likely to use a larger K and a larger L. So here is actually a trade-off between space and query time versus the effectiveness, because when K and L, especially L, becomes larger, right? We need more space to store the hash values, or to create, because we need to create L different hash tables, which we will see later. I will give you the detailed implementation framework of LSH, but basically L corresponds to the number of hash tables as an index. So when L becomes larger, we will need more space, and we will need more time to do the retrieval on these L hash tables. But we do have a better effectiveness of our LSH scheme. Right. So false positives and false negatives of LSH. So basically, by saying false positive, we actually mean the returned data with distance between O and Q that is larger than R2, or say those far away points, or this similar objects, right? If we use Jaccard similarity. So these points are not supposed to be returned, right? But they has been returned, or as a candidate. That's why we say it is a false positive. Positive means they are returned. False means they should not be. So they should not be returned. So similarly, for false negative, negative means they should not be returned. Negative means they are not returned. And false means this should not happen. So they should have been returned, but they did not. Why they shouldn't have been returned? Because the distance is smaller than R1. or these are the near points or similar objects, right? So in this example, if we use 0.7, 0.8 as the threshold for the dissimilar and similar objects, so this green part, this area represents those false negatives, right? They should be returned because the similarity is larger than 0.8, but they did not. They have not been returned because this curve here is not large enough. It's not close to 1 enough, right? So the red part here represents the false positive, right? They should not be returned as they are smaller than 0.7, but they have been returned, right? Because this curve, the part here is not close to 0, not as close to 0 as possible, right? And again, in this case, if we tune K and L, as you can see, we are actually change the fraction of or the size of this false positive area and the false negative area, right? For example, in this case, with a smaller I but larger K, right? We can control the false positive to be very small, but for the false negative, there would be a large part of the false negative. Or say, in this case, let's say it's almost half, or just a little bit less than half of the objects that should have been returned but have not. Right, so a huge false negative. But if we do it inversely, we use a small k, we even don't need a very large L. As you can see, the false negative is quite small, but there is a huge amount of false positives. Because basically you are include, let's say, half of the area for those smaller than 0.7 objects, right? Those objects, the similarity is smaller than 0.7. Well, again, as I said, it's a trade-off between the time and the space versus the effectiveness, or say the amount of false positives and false negatives, right? It is also related to your application. I mean, in some applications, false positives is allowed, but false negatives is not welcomed. For example, you say if you, this example is good. For example, you search for the answer to your homework online, right? You don't want to miss any chance to find the correct answer, so you are willing to throw some time on verifying all the returned retrieval results, right? Even some of them are irrelevant. So these are the false positives, right? But it's okay. I mean, you are willing to spend time on the verification, and on the other hand, you really don't want to lose any chance to find the real answer to your homework, right? So in this case, you want the false negative to be as small as possible, but you are willing, you can allow more than some more say false positives. Okay, and this is a more natural case. I mean, usually people are willing to accept false positives, but they don't willing to accept false negatives. Right. All right, so let's come back to the slides again. The framework of a nearest neighbor search using LSH. Well, again, this part, due to the time limitation and also the mathematics between LSH is really complex, so I won't introduce them or discuss them in this lecture, in this course. If you are interested, you are welcome to do your own research, or you can contact me. I mean, I can throw you some paper for you to figure that out. So take the theoretical part of LSH away. Here is the framework of how we are going to use LSH to solve our problem. So basically, for the pre-processing part, we need to generate LSH functions. Right? We have introduced 3 different LSH functions: the min hash, sim hash, and p-stable. Again, p-stable is the most important one because the following 2 variant of LSH are all based on this p-stable one. All right. So for pre-processing, we generate LSH functions. How many LSH functions do we need? We need k times l LSH functions, right? And for the index part, for each I in from 1 to l, we compute hi of o for each data object o. So that means for each data object o, we would have h10, h20 till hlo. Right. So it's l hash values or super hash values. Now we index o using HIO as the key in the ith hash table. So we would have L hash tables, and for the ith one, we index O using HI of O, O's super hash, O's ith super hash, super hash. Okay. So for the after the index, we would have L hash tables. What is the key? The key is HIO, right? And the value is O, or say the ID of O. Well, we usually use the ID of O because if we store the original O, we don't need to store original O for L times, right? We only need to store them for once, and we use the ID to refer to them because each O is a high-dimensional data. It occupies much more space than a single integer of the ID, right? So this is the index part. For the query part, well, we compute HIQ for query Q using I from 1 to L, right? So we compute L hash super hash values for the query Q. And then we generate the candidate set. So to generate the candidate set, O can be a candidate if there exists an I from 1 to L either I from 1 to L, the superhash of Q and O are the same. So O shares the same superhash out of this L superhashes, right? Shares at least one, it becomes a candidate. So we can have the candidate set. Then we do the verification. So we compute the actual distance or similarity for all the candidates and return the nearest one to the query. So as I said, I mean, it is possible that we are not returning the nearest one. So what we have returned is a approximate nearest one. And thanks to the theoretical guarantee of LSH, where we although we won't introduce it in the class, so basically it helps us to obtain this approximate nearest neighbor of the query with the probability larger than 1 minus delta, or say a constant large enough probability. All right. So this is the framework of solving a nearest neighbor search using LSH. And now it is a little bit confused, so if you have any questions, welcome to ask. And also during this explanation of LSH, sometimes I use Gcard as an example, especially when we're talking about the numbers here, or we talk about the curves here. Includes my my example using GeoGebra. It is because for Gcard similarity, or say min hash, it happens that the probability equals to the Gcard similarity, so it is more straightforward. But you can understand that this is for similarity, and for distance, it's basically the same thing, but the formula is a little bit complex. So as you can see, the figure of the curve of the functions, of the probability would be a little bit different, but all in the similar trend, or the or symmetric to the, for example, for sim hash is actually symmetric to min hash, and for p stable is actually similar to sim hash. It's more like already applied and right on the sim hash, but basically the trend would be the same. And as we have discussed before, you can always tune L and K to create the curve that you want to have. All right. Here, this table has nothing to do with either Gcard or Euclidean space, Euclidean distance. This PQO, it actually refers to the PQO. Let me see. It should be something. Sorry, it refers to the probability here, but here you can actually use similarity to replace the distance. It does not affect the conclusion of this whole thing. Okay, we just use Gcard as an example here. So I do hope that you don't mix two things up together. They are kind of different, but within this LSH context, they are close. Let's look at the drawback of LSH. I mean, we have talked enough about how good LSH is, but LSH does have its own drawbacks, and that's motivate the researchers to come up with new solutions to improve LSH. So ideally, I mean, during the, I'm not sure if you have noticed this or not. For example, I think the first one is quite straightforward. The concatenation of two hashes to form a super hash is kind of too strong, right? Because, well, even any for for any j, if this hij of O1 and hij of O2 are different, it will lead to the difference or unmatch of the super hash. Right. You can consider like, for example, the query is if k equals to 5. This is for one super hash. The query is O1, and for a data, it will be O1, but just 1, 0. So you can imagine that in this case, this 0 should be really close to 1. It does have a high chance to be the same. To be at least a candidate of the nearest neighbors of Q, but it loses such chance because of this. Well, it is true that in LSH we do have a makeup that is to use multiple hash tables. That is what L stands for. But still, I mean, it's kind of, at least it is inefficient to miss such kind of possible candidates. So that is one thing, or one observation that we have for the drawback of LSH. Another is that the LSH is not adaptive to the distribution of the distance. Well, it is true that we can, by tuning K and L, we can control the curve of the probability that O becomes a candidate of Q. That is true, but when we have built the index, everything is fixed. Everything is fixed. So it happens that, for example, we're not getting enough candidates, or sometimes we're not getting even any candidates because we have already set this Q and this K and L, and also, I mean, we don't know that the nearest neighbor of Q, what is the distance, right? So the distance between O and Q, we don't know what it is. Right? So that is why sometimes we do have the possibility that we have not enough candidates. So in order to solve that problem, we need different W. Usually we build index using different W. Otherwise we need to tune W for each and every query. So that is apparently infeasible. But even with multiple Ws, even build multiple indexes with different W, it's a waste of, or at least quite consuming, quite space consuming and time consuming for the index construction. So for LSH, or the improvements of LSH, we will introduce two algorithms. One is a multiprobe LSH, and the other is C2 LSH. So both algorithms aims to solve the problem on the background of using Euclidean distance. Right. So we are talking about p-stable LSH. So just to refresh you, and which is quite important when we discuss the intuition and motivation of these advanced LSH algorithms, the p-stable LSH, the idea is to project the points to a one-dimensional line using AI transport x plus bi divided by w, and we do use a floor function. The floor function is to bucketing or partition the line here, right? So for example, the green and purple one will be will have the same hash value as it lies in the same, we call it a bucket. Call it a bucket on this line. Right. And for example, the black one does not share a hash value with any of the other three points. Right. So this bucket concept is quite important because the observation of multiprobe LSH is that, say, if Q's nearest neighbor does not fall into Q's hash bucket or the same hash bucket as Q, then most likely it will fall into the adjacent bucket to Q's bucket. Right. Here we do have the, this observation does have the support from mathematics, right? So basically, we know that the hash function would be AIXI plus AIX. No. Let's consider a single hash function. It would be A transpose X plus B divided by W, and we take a floor function here. So if we remove the floor, and we consider another Q, so it's A transpose Q plus B divided by W. If we do the minus, so we see what's the difference between these two. It would be A transpose X minus A transpose Q. This 2B has been eliminated and divided by W. W is a constant number, so we don't look at it as well. So this is what we have. So this, which is actually this one, actually follows a normal distribution, because the two stable property of normal distribution we have introduced before. So this one follows the normal distribution that the mean is 0 and the standard derivation would be the norm of the x and q to the power of 2, which means, let's say this FIQ is actually this. In the paper it's actually plus B, but as I said, the B does not really matters. So here is that the difference actually follows a normal distribution, right? So if we put FIQ here, it's actually the center of the normal distribution, and these are, for example, here the x-axis represents the difference between A transpose X and A transpose Q. All right. So if we say this is a bucket, then if this X does not fall into the same bucket as Q, according to the property of normal distribution, the best chance, or the second highest probability, is the adjacent buckets of Q's hash bucket, as you can see here. So the idea here is quite straightforward if we have this observation. So the idea is to not only look at the hash bucket where Q falls into, but also look at those hash buckets that are adjacent to the Q's hash bucket. So it's Q's neighboring slots, or the adjacent hash buckets. They're all referring to the same thing. All right. So, but the problem here is that if we consider in LSH, because here we are still discussing one single hash function, or a single LSH hash function. But in LSH, we concatenate k of them together, right? So for each of we concatenate k together, and for each of them, we need to look at the adjacent bucket, which is for each of them we will look at two adjacent hash buckets. And remember, because we concatenate them together, so at each time we can only pick one of them. Say, for example, we pick this one and this one and this one, and for the rest we just pick the Q's bucket. This is a new super hash. This is a new super hash. So in total, we would have here should be 3. We would have 3 to the power of k. We would have this much different. It should be super hashes. And when k is, so we will increase the search time cost on a single hash table from 1 to 3 to the power of k. So even for a normal k, usually the k is around 10. They are around 10. It is still quite large, right? And on the other hand, I would say that they are not even equally important. For example, you can imagine that let's say this is a bucket, and this is when the query, the projection of the query lies on. So apparently, for this bucket, the 2 adjacent buckets, this is the HIQ. This is, let's say it's HIQ plus 1 and HIQ minus 1. So apparently, the probability of the Q's nearest neighbors lies into this HIQ plus 1 is much larger than the probability that they lies into HIQ minus 1. Right? So with this observation, that we do have a better solution to then naively, enumerate all 3 to the power of k different super hashes, right? So we would have a break. We would stop here and have a break, and then we come back, and we will discuss the solution of multi-probe LSH, and also we will introduce C2 LSH. Also, C2 LSH is what it is what you are supposed to implement in the project, so it's quite important.